Okay, in this set of notes, we're going to look at two probability distributions that are discrete, that are specifically used on the AP statistics exam. One is what we call the binomial distribution. The other is going to be what's called the geometric distribution. They're fairly useful and they're easy to perform calculations with. So I'm going to break these things out and try to get you to understand them one at a time. Okay, so the first thing we need to do is we need to understand the two different situations. So they're going to be what we call the binomial setting and what we're going to call the geometric setting. Okay, so in the binomial setting and the geometric setting, they're very similar. You have, in both settings, you have independent trials. Dependent trials. And you have two outcomes. So in both settings, you have two outcomes. We call one outcome a success, and we call the other one a failure. Now, don't think that failure is always bad. I mean, like, failing to die of COVID is good. Success is not always good. Succeeding in having a car accident is not necessarily good. But these are two different possible outcomes, success and failure. Okay, so under the binomial situation and the geometric situation, the probability of success, which is what we call P, is fixed. So on each trial, the probability of success is the same. So we're not going to deviate from that. The key here is what happens in the when we get to the random variable. The random variable in binomial counts the number of successes out of n trials. Okay, so x is the number of successes out of n trials. In geometric, y is the trial on which you have the first success. Okay, so here it's a fixed number of trials, n. Here it's how many trials do you do before you get, well, how many trials do you have to have before you have your first success, right? So this is like, could be up to infinite, but this is a fixed number. Okay, so binomial is actually slightly easier to wrap your head around than geometric, but they are both pretty useful. All right, so let's kind of play this out. We're going to kind of create an example for each, okay? So let's come up with a binomial example. So let's say that we have a 10 question test, right? And we want to know, there are 5 answer choices for each question, right? So this is a multiple choice test. You have a 10 question test. There are 5 answer choices for each question. The probability of guessing the correct answer is 1 in 5, or 0.2 for each of the 10 questions. So in my binomial example here, my number of independent trials is 10, and I'm going to guess on every single question, and my probability of success is going to be 0.2. Now, there is a crazy complicated formula that you can use to get the probability of having a certain number of successes here. So if I think about this, my binomial distribution is going to set up with x being the number of successes. So how many questions do I get right? And this is the probability that x is going to be that value, right? So I get a 0, 1, 2, 3, 4, and I'm just going to keep counting out to 10, right? So let's say I want to find the probability of getting 2 successes. So the probability that x is 2. Okay, so if I roll over to the notes here, right, so if I go over to the notes and I scroll down a little bit here, it tells me that it's this crazy formula here. That the probability of x being 2 is n choose 2 times p to the 2 times 1 minus p to the that's going to be p to the, p to the 2 times 1 minus p times to the 8th, right? Because that's going to be 10 minus 2. And this n choose k is this weird formula of n factorial over k factorial times n minus k factorial. And you can spend a lot of time like sorting that out. And why does that work? I'm not going to spend a lot of time on that today. Okay, we might take a deep dive and look at that later. But according to this formula, I'm going to get that this is 10 choose 2 times the probability of success, which is 0.2, times the number of successes, 2, times 1 minus 0.2, times the number of failures, which would be 8, right? So if you kind of think about what's going on here a little bit, it'll make some sense. If I got 2 questions right, I take p, my probability of success, and I take that to the second power. 1 minus 0.2, which is the probability of failure, some people call that q, which is 1 minus p, right? And you have 8 failures. But this would be great if like you got the first 2 problems right and everything else wrong. But see, that's not the case. I could put those first 2 in different places. So the number of different ways that I could get 2 right is 10 choose 2. This is also, you've seen this as 10C2 at some places in your reality. So like I can actually use the calculator to get this. Now it also gives me this crazy formula for this, right? It tells me that that formula is n factorial over k times n minus k factorial. Okay, so let's do that. So that would be n factorial, so that's 10 factorial over k factorial, so that's going to be 2 factorial times n minus k factorial, so that's 8 factorial. Okay, so if I was going to do this like all the way out by hand, so let's get my crazy calculator out here, right? Put that next to it. Okay, so let's put that next to it, right? And so I can quit, go to my main screen, clear this all out. I could find that number up front, right, by going like 10 math factorial, right, divided by 2 math factorial, okay, times 8 math factorial, right? So that's the binomial coefficient times 0.2 to the power, let's get that parenthesis there, 0.2 to the power of 2, and then 1 minus 0.2, right? So 1 minus 0.2 to the power of 8, and that comes out as 0.3. So this whole thing comes out as 0.302, roughly. Okay, so what am I going to do here? So if I'm looking at my little chart here, what I just found was that the probability of getting 2 of these correct, 2 of them correct, is 0.302. Now, that's really convoluted and complicated, right? So what I'm going to do is I'm going to show you how to make this a little simpler. So I'm going to show you where the binomial distribution is. So if I go second vars, and I drive down a little ways here, I get to the binomial PDF. So note I'm using the PDF here, right? Binomial PDF. How many trials do I have? I have 10. The probability of success is 0.2. The probability of me getting 2 correct is what I want. And I paste, and I hit enter, and voila, it gives me the same number without having to punch in all of those calculations. So let's say I wanted to know the probability of getting 3 correct, right? Or let's say 5, right? So I go back down to binomial PDF, right? 10 trials, 0.2 is the success. Getting 5 correct would be 0.2, so about 2.6% chance. All right, so hopefully you're following me on that. All right, so what if I want the whole chart, right? Well, I could do this. I could go stat, edit, right? So I got a bunch of stuff in here, so let's clear this all out. Clearing. All right, so let's clear everything out. I got a bunch of stuff in here, don't I? All right. Clear. All right, so let's go and put the possible outcomes. 0, remember, you can have no successes. You got to put 0 in there, right? 3, 4, 5, 6, 7, 8, 9, and I could have 10 possible. I could get them all right, right? So here's what I'm going to do. I'm going to go back to the main screen. So I'm going to second quit. And I'm going to say, let's get second vars, binomial PDF, right? And I'll put in 10 trials, probability of success is 0.2. And then I'm just going to say, let's put L1. So I'm going to put all the L1s in there for the X values, right? And then where do I want this to end up? So I'm going to store that in L2. And boom, done a bunch of calculations and stat, edit. Boom, there's my whole chart. The probability of getting 0 correct, 1 correct, 2 correct, 3 correct, 4 correct, so forth and so forth, all the way down to 10. So I could make that whole chart for my problem. Okay, so this is why the binomial PDF is really important. Okay, just so we're aware of what the binomial CDF does, the binomial CDF, not normal, quit, binomial CDF, right? I can go binomial CDF will allow me to go up to a certain number. So like 10 trials, the probability is still 0.2. Let's say I want to have the probability of getting 5 or less correct, right? So I'm going to put in 5, and I'm going to get a really big number there, right? It's like 0.99. The probability of getting 5 or less correct is going to be 0.99. So did you hear that? It's 5 or less. The CDF gives you everything up to that number. Okay, so if I wanted the probability of getting, let's say 3 or less, I would put that in there. So the probability of getting 3 or less correct is actually 87.9%. So this is not really easy to get many correct on our multiple choice test here, right? All right, so kind of looking at our notes here, we've defined what the binomial setting is, what a binomial random variable is. We've kind of worked our way around this binomial coefficient and binomial probability formula. I mean, you can do this by hand. I don't recommend it, okay? So the nice thing about binomial is that the mean and the standard deviation in this setting are really easy to find. So the mean is the expected value. It's the number of trials that you would expect to get successes on. So like, you know, if I have this 20% chance of getting it right, how many out of 10 should I expect to get right? Standard deviation gives me an idea of how that spreads, right? So let's kind of take a look at how that works, right? So one of the nice things about the binomial distribution is that the expected value in this case is just n times p, right? So if I have 10 trials with a 0.2 chance of success, and I go and I say, okay, so what is 0.2 times 10? And that tells me 2, right? So if I have this, I would expect to get 2 correct, which 20% of 10 is 2. That makes sense. So what's my standard deviation, right? So my standard deviation here, according to the notes, is n times p times 1 minus p, and then I take the square root. You could also sometimes read this as n times p times q if you let q be the same as 1 minus p. That's the probability of failure, right? So in this case, this is square root of 10 times 0.2 times 0.8, and that would be square root, because we're taking square root of a variance, times 10 times 0.2 times 0.8 gives me roughly 1.26. So my standard deviation for this example is going to be around 1.26, right? So on average, we're going to be within 1.26 trials of 2, right? So if we get below 0 or above like 3.5, we're starting to get into more unusual territory here. Okay, so there's something that's interesting that's going on here. Okay, if you take a look at these distributions, they tend to be high near the mean, and they tend to kind of move out from there, which means that there is this kind of relationship that's useful for a binomial to model a couple of different things. The first one is when I'm dealing with a large population. Okay, so in theory, if I am asking different people from a large population a question, right, these are not technically independent trials, okay, because if you kind of think this through, let's say there's exactly, which I know this is not true, exactly 350 million Americans, right? And then I'm going to ask like 4 of them whether or not they're Democrats, right? So what happens here is that there's like the number of Democrats, right? And there's the number of Americans. And each time I ask somebody, I have to pull them out of the pool, right? So the number of Democrats goes down by 1, and the number of Americans goes down by 1, which means that the second trial is, because there's no replacement in this, is like going to be different from the first trial. But if you kind of think about this, when I'm dealing with a large population, it's really not going to change by much. Okay, like, 180 million out of 350 million is not going to change a whole lot from 179,999 million out of 349,999 million, right? So the question is like, when can I treat the trials as independent, right? So when do I assume that, like, though I don't have it, I can pretend like I'm in the binomial setting? And the answer here is a thing called the 10% rule. Okay, so this 10% criteria. And basically the rule is this, is that if my sample, n, that's my sample size, little n, and my population size, big N, are such that the sample is no more than 10% of the population, then I can treat the trials as though they are independent. Okay, so I can just like work this out as though I meet all the conditions of the binomial reality and I'm good. Okay, so that's good. So when I want to do something with a large population and I want to apply the binomial setting to that, if I check the 10% criteria, that the sample is no more than 10% of the population, then I can assume independent trials. Okay, second thing that's going on here. It also seems like I should be able to, when I have like big situations where like I have hundreds of trials, right? So let's say my number of trials is like 100, okay, and my probability of success is like 25%, right? It feels like I should be able to substitute the normal distribution here, because this is going to be like somehow symmetric and bell-shaped with a mean where the expected value is, which is the 100 times the 0.25, which is going to be 25, with the standard deviation being square root of 100 times 0.25 times 0.75, which is going to get me, let's see what that is, square root of 100 times 0.25 times 0.75, right? That's going to give me 4.33, so 4.33. And what I'd like to be able to do is to say, like, what's the probability that the number of trials that I get a success on is between, like, I don't know, out of 100, let's say 75, or is it less than 75, right? So what's the probability of that? Well, I could run the binomial CDF here, right? So, like, let's see what happens if I run the binomial CDF. 75 or less, right? So let's make it less than or equal to 75 successes, right? So if I run the binomial CDF here, I go second vars binomial CDF, right? So I have 100 trials. Probability of success is 0.25, right? And I want to have 75 or less, and this gives me 1. Wow, so that's like way more. So let's make it something less ambitious than 75 out of 100. So let's say it's, I don't know, let's say it's more than 30, right? There we go. I like that. That's a little better. Probability of being more than 30. So instead of putting 75 there, we'll put 30. There we go. Aha, there we go. So that's better. 0.896. 0.896. Okay. The 1 is like, it's almost certain to be below 75. If you think about this, at a 25% chance of success, the chance of us getting less than 75 is like dang close to 1. And when it did it, it rounded to 1. That's what happened there. So my question now is like, if I have this, and I said that the mean was 25, and the standard deviation was 4.33, then if I assumed normal distribution with a mean of 25 and a standard deviation of 4.33, what is the probability that I'm going to get less than, that I'm going to be, oh crud, I have this backwards. X is less than or equal to 30, sorry. Okay, so this is the problem, because it's cumulative up to 30, right? So the probability that X is less than or equal to 30. Could I use the normal distribution to do this? So let's see what happens. So I go second vars, normal CDF, right? So I'm less than 30, so I need an extreme value here, right? I'm going to go up to 30 with a mean of 25 and a standard deviation of 4.33. And, what did it not like there? Negative, not minus. There we go. All right, so it's giving me like 0.876. Now the question is like, these are close. Are they close enough? And, 89.6, 87.6, they're pretty much close enough for all intents and purposes here, right? I mean, we're off by maybe 2%. So can we use the normal and binomial to approximate each other? And when are we good enough to do that? Well, there's a rule for this, and there's a rule called the law of large counts. And the law of large counts says that n times p has to be greater than 10, greater than or equal to 10, and so does n times 1 minus p. Or another way of saying this, n times q, right? So in my example here, n was 100. My p was 0.25, which gave me 25. My n here was 100, and my 1 minus p would be 0.75, which gives me 75. Both of these numbers are bigger than 10. So I've met the law of large counts, and this says that I am close enough that binomial and normal can approximate each other. Now, in our technological big world, like, when is this useful? This is useful when you're working with really large populations, okay? You don't really want to play binomial games when you have a really big population. It would be much easier to just work it off of a normal distribution once you know what the mean and standard deviation are. Okay, so that sets us like way adrift here. But let's get back to the main premise. All right, so binomial is independent trial, so two possible outcomes, fixed probability of success. X represents the success out of each trial. We used the binomial PDF, right, to be able to figure this out. Geometric is very similar, but geometric asks a slightly different question. Here, y is the number, well, the trial number, the first success happens on. So, what's useful here is we can get a probability that y is some value, right? So again, you have like a probability distribution here. Y, probability of y is that value. So you could have the trial in the first, you could have the success in the second, the third, the fourth, but this just could keep going on and on and on forever. Okay, so how do we calculate this? So let's take our situation again, where we no longer have a 10 question thing, we have an infinite number of questions. We're just going to keep asking questions, and we're going to give you a 20% chance of getting it right until we get to the first correct answer. Well, the probability of getting the first one correct is 20%. That makes sense. Probability of getting the second one correct, well, that's going to be getting one wrong and one right. So that's going to give me 0.8 times 0.2, which is going to be 0.16. Okay, so like, what's the probability of getting on the third one? Well, I'd have to get two wrong and one right, right? So this is going to be 0.8 squared times 0.2. Oops, I need times in there. Times 0.2. Right, so this means I'm going to now at 0.128. Okay, so we're dropping. Well, I mean, like, I could do this all day. So the formula, if you think about it, is going to be the probability of failures, that's 1 minus p, sometimes called q, times the number of failures. So that's going to be, like, we'll call it y minus 1. I think I used k in the formula in the notes, times p, right? Because you only get to be successful once. So, is it going to work that this exists in our calculator the same way? So let's focus in on the 3 here, right? We want to know the probability that we get it on the third trial. So, lo and behold, we go to the calculator, we go second vars, and we go down to the geometric PDF, right? Probability of success is 0.2. Probability of getting it on the third trial comes out as 0.128. So again, the challenge here though is you can never create the whole chart because it just keeps going on and on and on and on. Like, I can get the geometric probability of geometric probability of 0.2 with, let's say, the first success was on the 5th trial. And that's going to happen 8% of the time, right? But the first success could happen on the 99th trial. So this is part of my problem. So this is where, like, this CDF becomes really important. Because, like, let's say, well, I can get, like, the probability that happens in, like, the first 3 trials, right? So 1 vars, go down to the geometric CDF, probability of success is 0.2. I want to get the probability that happens within the first 3 trials, and that's going to give me that first 3 trials. And if you look, that's 0.2 plus 0.16 plus 0.128 adds up to that 0.488. So that tells me that I got it within the first 3 trials. But what if I want to know how long, like the probability that it's going to take me more than 3 trials? Well, that's when you're using your idea of complements. So you take 1 minus that geometric PDF. So you can go 1 minus the geometric PDF that I got it within the first 3. So this should return the probability of that it's going to take me more than 3 trials, and that's going to be that 0.512. So this is why that geometric CDF matters. Now, if you look in the notes there, they're going to give you the expected value for the mean for the geometric distribution. They don't give you the standard deviation. It's a little more complicated than what we need for this course. But expected value is really simple. Expected value of y here is just going to be 1 over p. So this is going to be 1 over 0.2, which means that I would expect to have my first trial, let's see, 0.2 is 20%, so that's 1/5, so it should happen on the 5th trial. So I would expect to get the first one right on the 5th trial. Now, does that mean it's going to happen there? No, but it's the most likely trial for it to happen on. All right, so let's kind of recap real quick here. 2 major distributions, binomial, geometric. They both have the same basic premise. The premise is that you have independent trials with 2 outcomes, one's success and one's a failure. The probability of success in each trial is fixed. The only difference is that the binomial is a fixed number of trials, and you're going to try to figure out the probability of getting a success on how many trials. In geometric, you have an infinite number of trials, so you want to know which trial you get the first success on. All right, so we're going to look at some problems with these in the next class, and that's it for today. Okay.